All right, for number 9, guys, we need, I know I just said this, but not while recording. To solve this equation, you need to have, to solve this problem, you need to have this equation, velocity equals angular velocity times radius. So here is, here's how this equation works. So imagine you're looking at something rotating from above. So say it's like me swinging my keys around. So like I'm standing right there in the middle. You're looking at this from above. My keys are swinging around on a rope, okay? Or some object is swinging around like this. Now, if you have an object that's rotating around like this, every single point, whether you're close to the center or away from the center, so put a small circle there and then a big circle. What do these 2 points here have in common? These 2 points will have the same angular velocity. So just think about it. Like if the angular velocity here were 2 revolutions per second, what would be the angular velocity of this inner point? 2 revolutions per second. What would be the angular velocity of this outer point? 2 revolutions per second. But the linear speed, which later on we're going to refer to this as a tangential velocity. Tangential just means, like, look, like say it's my keys flying around here. My keys are going around. What if suddenly the rope broke? If the rope suddenly broke, how would the keys or whatever the object is, how would they leave the circle? They would leave the circle how? Tangent to the circle. Like, so what if the keys left right here? Tangent to the circle. So tangential velocity, it's a linear velocity. It's measured in meters per second. So anyway, back to my point. My point is this: when you have an object rotating around, like we do here, we have the blades of a helicopter spinning around. Every point, whether you're close to the center or away from the center, has the same angular velocity. But as you move farther and farther from the center, what gets bigger? This linear velocity. You know, a point out here has a bigger circle to get around than a point in there. But they're both getting around in the same time. So the point farther away has to be going faster in a linear sense. Not in an angular sense, but in a meter per second linear sense. Okay, so this is the equation that applies to this problem. The one catch to this equation is you have to be in radians when you're using it. The angular velocity, this has to be radians per second. Okay, so here's the given info. We got the radius of the 2 helicopter blades and their angular velocities. So what we have to do is we got to convert these angular velocities into radians per second. So we got revolutions per minute. So how do you convert that to radians per second? Well, like this. 1 revolution is what?
2 pi radians.
2 pi radian. The revolutions cancel. Minute goes up here. We want to cancel the minutes. Go to seconds. That's 60 seconds. So for the big one, let's see. This comes out as 47.12 radians per second. So this angular velocity is 47.12 radians per second. Huh? Hey, guys. Are you?
14 ounces.
Wow.
Is that 14 ounces? I'm trying to read this.
That's like,
Got the picture of this.
wow. Hold on. Guys, Coleman just had his baby. Let's finish this. Yeah, Coleman had his baby. All right, shh. So, calculate the speeds of the tips of both rotors. So we're going all the way out to the tip here, the tip of the rotor. So what are we going to plug in for R? The full radius, right? So for the big blade, we're going to go angular velocity. So that's 47.12 radians per second, multiplied by the radius, 3.8 meters. The tip of that big blade is rotating at 179.1 meters per second, right? That's for the big blade. Now, do the same thing But for the little blade, we go, oh, dude, we got to convert that. Did we not do that? Hey, this converts out to 433 radians per second. So you go 433 radians per second, and then the radius there is 0.51 meters. So this gives us a linear speed of 221 meters per second. Okay?